So while they're preparing, let me introduce Congyue. So Congyue Deng is a postdoctoral fellow at the Schwarzman College of Computing at MIT, working with Kai-Ming He, William Freeman, and Marin Solzhenitsyn. She obtained her PhD in computer science from Stanford University, advised by Leonidas Kibas, and her research interests include 3D computer vision, geometric deep learning, and physical representation learning. So with that, the floor is yours. Thank you.
Thanks for the introduction and thanks for the invitation. I'm very excited here to present about my research. So today I'm gonna talk about this work, Denoising Hamiltonian network for physical reasoning. So there are three words here, like denoising, Hamiltonian, physical reasoning. I omitted the word network because I'm just in the area of deep learning and everyone works on networks. And I'm gonna start with a little bit background for general things. So basically, for physical systems, you also have a temporal system, like you have some observations at each time step, and you have a sequence of time steps. So this is a general problem of sequential modeling. And there have been a lot of sequential modeling works in the community. For example, there's the general black box networks, like the very large video diffusion models, for example, or other transformers, where people believe in that you can do pure data-driven things, like you have a very large model, maybe you don't care too much about the priors in the network architecture, and you train that on a lot of data, and you learn something, you learn some distribution from the data. And on the other side, there's also another extreme where people build physics-constrained operators into neural networks, like you have some physical structures or physical laws that you get from some physical principles, and you just construct operators based on that and build that into networks. So these networks are usually they satisfy some very strict constraints of physics, and you can apply them to some problems following those constraints. But on the other side, sometimes they're probably too limited, that sometimes people find it a little bit struggling to really scale up these kind of networks. So the question we're trying to discuss here is what are the things in the middle? So what we can get in the middle. And for example, if you go from the black box side to the operator side a little bit, what are the little bit constraint you can add, but without limiting too many things? Or from the other direction, you go from the operator side to more black box things. So what are the things you can relax here? And if you relax something there, you're probably hoping to gain something from the relaxation. And what are the things you can gain from there? So this is a general question we hope to ask or discuss in this work. Okay. So following these intuitions, we did some initial studies into these problems, and specifically, we proposed a denoising Hamiltonian network for physical reasoning, not for images. That is just an analogy on the top. So specifically, we're drawing inspirations from looking into a computer vision history, where we had a convolution operator in the past, and then we had a convolutional neural networks. If you think about that, before transformers, convolutional neural networks, they probably really worked so well for image or all kind of image-related data, also including videos. And how it came, where it came from the convolution operators in mathematics or in physics. However, when people build convolution operators into neural networks, people didn't do things like you have this operator, you directly put it into a network. Why? Because at the time there weren't so many neural networks, probably only MLPs before convolution neural networks. I mean, also a few others. So what people really did there is that you had a convolution operator from mathematics, and you turned that into a neural network by doing what? By saying that you have this hyperparameters called the kernel size, and you also have the hyperparameters called the stride. And then you define these hyperparameters by extending the convolutional convolution operators, and you stack so many. You stack, for example, 128 such operators together, and you call this a convolution layer in your network. In such a case, you're still keeping the translation equivariance, which is a structure of the data, in the network architecture. But on the other side, compared to what people did in mathematics or numerical computation, you did a lot of extensions. And what are you gaining from that? Basically, you get a lot of flexibility and also high-level reasoning from that. So beforehand, with only the mathematical convolution thing, you can do some low-level image processing, like denoising or deep blurring kind of thing. But now with the extended operator and with the optimization in the framework, you can learn some black box things, and you can have probably telling whether an image is a cat or a dog, or probably you can also do some high-level vision reasoning. So the question, or the analogy we're trying to make here is that we have a lot of physical operators from the PDEs or ODEs or the physical principles. Can we also make a little bit extensions to these operators to still keep some essential physical structures in the operator itself, but we also want to relax a lot of things to make it more learnable into something that can probably do a little bit higher level physical reasoning from the physical data. So specifically, we're following the Hamiltonian equations in physics because it's kind of like a generalization of the Newton's laws, which is kind of general. And it's also like a good way of describing conservation laws in physics. So I'm probably going to skip the mathematical details. But basically, you have some physical equations like the Hamiltonian equation, which is also actually used in control. And you have some discretizations of that. For example, you can discretize the time steps between time step t and t+1, and you can do some computations to compute the state transitions. So specifically, okay, what we're extending here, first of all, we are replacing the numerical computations between adjacent time steps into a more general sense. Specifically, we call this a blockwise Hamiltonian. So we're doing two things. One is that you have the delta t in the numerical computation, which is super, super small. But now we're saying that how about we just treat delta t as a stride in the neural network? So now it can be arbitrarily large. And also, we're making it blockwise, so we're grouping a number of states together to do some more unifying computations. And moreover, we're having this denoising process. So instead of always inferring from xt to xt+1, we're hoping to have more flexibility along the temporal dimension. So specifically, we're training this denoising at arbitrary order. And what you can gain from that is that by designing different patterns of denoising, you can do different types of inferences. So for example, you can do an autoregressive manner, which is more like a standard type of simulation, like you know the present and you want to predict the future. But on the other side, you can also do super resolution by masking out the things in the middle, so you're filling things in the middle. So that is probably useful for some experimental data processing. And finally, doing some random masking, following the sense of MAE or BERT in vision or language. We can probably also do representation learning, where we can try to infer some higher level things from the tokens learned in the network. And a little bit analogy here is that, so you have physical equations or numerical computations, you have these things, which are the operators, and you have the black box models, which is the deep learning framework. So you want to combine these two. How can you do this? One is that you can put the physical operators into the black box. But subtly differently, you can also turn the physical operators into a black box. So in such a way, you're no longer treating that extension as a relaxation. You're not feeling that you're losing something there. But on the other side, you're extending it to handle more general scopes. And a brief summary here is that, so basically, the high-level idea is that we're replacing the numerical computations in, for example, beforehand you have neural networks and you have numerical solvers, and you learn something, you learn some physics-inspired neural networks, and you probably still need to put the network into the solver. So now the thing is that we're trying to absorb everything in the numerical computation into the network. For example, you have delta t, you turn it into a stride. You have the variational integration process at test time optimization. You turn that into a learned denoising process in the network. So in such a way, you're absorbing things into the architecture, and you're no longer having additional numerical computations outside the network, but you're still keeping the basic physical structures in the neural network. And it's for experiments, so what we're gaining from the network architecture is that we have better flexibility, and we can potentially also do higher level reasoning. So specifically, we tested our network on different kind of tasks. Due to time limit, I probably need to go very fast. So for example, forward simulation, where you know the past and the present, and you want to predict the future. And also, something exciting here is also about the representation learning. We do the mass modeling, and from that, we can learn some global physical properties directly from the trajectory data. And also, we can do super resolution with a different type of denoising pattern. So with this unified framework, you can probably do a lot of physical reasoning tasks. And finally, I want to conclude my presentation with a little bit of discussion on this. So what we're trying to discuss in this work are these three questions. First of all, what is physical reasoning? A lot of works, when they talk about physical reasoning, is always about knowing the present and predicting the future, which is indeed a very important task. But probably when we're doing the prediction, we can not only predict xt plus 1, but we can also try to work with the trajectory in a more flexible manner. Second is following this question, what is physical simulation? Physical simulation is probably like you want to simulate some trajectory data of a physical system. But again, why you have to simulate that system from x0 to x1 to x2, et cetera, for example, we're doing like video generation. You not always predict it frame by frame, but you can also generate the whole sequence at the same time. So following this, can we also have more flexible ways of working with the trajectory, but also keeping the physical structure in the network? And finally, what is the physical constraints we desire in your network? Do we want to like keep everything in the operator, or do we want something in the middle that combines the operator, the basic structures in the operator, and also the black box things in your network? And that's it. Thank you.
Nice talk, by the way, Congyue. Do you see, so what are the avenues do you think could make the current video generative models to be physically consistent?
Yeah, thanks for the very nice question. It's also a widely discussed problem among a lot of people. I guess like some people are probably like the OpenAI people will just say like have more training data, have a larger model, and buy more GPUs, and you will get it. But I guess like maybe at least like I think from one perspective, I don't think that's the most efficient way. And something I try to explore starting with this work is that probably like some general sense of consistency. So one reason like we're extending the Hamiltonian framework here is that the good thing about the Hamiltonian equations is that you can model conservation laws of physics with symmetries in the equation itself. So basically, if you bake some symmetries into the network, you get some conservation laws. But again, it's like that is a very manually designed manner. So something that I feel might be interesting is that, so you probably want some more generalized concept of conservation. For example, some semantic conservation. Like a lot of videos, like we think they're not physically valid, or some generated videos, we think they're weird because like some subtle things are inconsistent across the frames. So what if like we can have some more flexible architecture, which in the architecture itself, we enforce it to discover those things that need to be consistent, and then we enforce them in the generation process. I feel probably that could be something that helps. So, or maybe making an analogy is that even when people talk about like no priors in the architecture, or like pure, like only learning things from the data, still most people are talking about the transformers. People are not talking about MLPs. People don't really expect MLPs to like work so well just like by learning from data. So, and what is the difference between transformers and MLPs is that transformers, you have the multi-head attention, and you're encouraging the network to discover the relations across different tokens. So this encouragement is essentially helping the network to focus more on that aspect. So probably like I feel what could be interesting is that you don't directly enforce physics or like so strong physical constraint in the network, but you still in some way highly encourage the network to discover physical principles or physical conservations, and then apply that to data. I guess that could probably be more data efficient.
To follow up on the question and your answer, could it be that some of the mechanisms that we identified in the previous presentation with causality, explainability, things like that, could be some of those ingredients that you want to make sure that are in your model? So could that be a possible direction, or how do you see that?
Yeah, I think that's possible. Also, like causality is, I didn't like think about causality that much, but because like one of my lab mates is so passionate about like causality, so like we sometimes discuss, and I do feel it's very interesting because actually when I present this work in the physics group, they talk about like time reversal. So like sometimes like in some physical system when it's conserved, there's like the reversion of the time, but sometimes time cannot be reversed. So I guess like that's also where causality happens, and I do feel it is something interesting in the sense that I feel causality is something or some physical relations across frames, but in a way that where time cannot be reserved. And, sorry, reversed. Okay, yeah. I'm not a physicist, and I don't know other terms. Yeah, but I do feel it's quite interesting. Also, probably another like slightly related thing is that, so there's also like the Hamiltonian concept in robotics or in control theory, where you have that additional term R for optimization. And I feel that R is also kind of like something that, it kind of describes something that you do something and the system will react to your actions. So I feel that is also like some causality that we can probably consider here.
So while he's preparing for his talk, I'm going to introduce Dr. Mosharaf Chowdhury. He's a computer scientist at the University of Michigan, where he leads the Symbiotic Lab. His research focuses on making AI and ML workloads more efficient, with a particular emphasis on reducing energy consumption through the ML Energy Initiative. He has pioneered multiple research areas, including AI energy optimization, systems for planet-scale AI, and memory disaggregation. Major projects from his team includes InfiniSwap, FatScale, TPP, and Zeus, the first energy-optimal generative AI stack. And previously, he invented CoFlows and was one of the original creators of Apache Spark. With that, let's welcome Mosharaf.
Yeah, so I'm going to talk about something that is very pressing today. Unless you're living under a rock over the course of first 2-3 years, I'm sure you have seen some of these headlines or some variations of them. There's a lot of concerns about how much energy does AI consume. And it's very hard to avoid this type of studies nowadays, because even if you go back 5 years ago, when people started to train these very large models, we started seeing that the estimated amount of energy consumed to train some of these models could be in thousands of gigawatt hours. And then over the course of the years, it just kept slowly growing. And these are only estimations of models that are open weights that people can look at. The actual models that we use, I'm sure everybody is using some form of AI, or most of us. They are much larger. And the consumed energy for training is significantly more. And it's not just we are doing training. After training, we do inference, and each one of them have hundreds of millions, perhaps billions of users. So the energy consumption of AI on the inference side is even bigger. And just to get a sense of how big these numbers are, US Energy Information Administration sort of have these numbers where they say to get 1 megawatt hour of energy, you have to burn more than 1,000 pounds of coal. So now multiply that by whatever this number and whatever big numbers it becomes, it's probably going to fill this auditorium and many of these auditoriums to get that many coal, and then we have to burn them. And then we can get that much energy just to train a small model, which probably is not going to be very good anyway. And all of these energy, they are going to these big AI data centers. So this is a picture I got from Google. It's a small data center, honestly. I'm just picking on it because it has nice, colorful walls. But essentially, what we found that in 2024, the total energy consumption for all these data centers globally was about 1.5% of all electricity in the whole world. And the current estimate is by 2030 is going to double, and this is a conservative estimate, before all of these news that keep coming out every day nowadays. Yesterday, OpenAI, of course, announced they are going to add 10 gigawatt on top of whatever gigawatts they have already mentioned with NVIDIA and AMD, and now yesterday was with Broadcom. They are building their own chips. And the thesis of this talk is that this is all good or bad, however way you want to see it. It's only going to, get worse before it gets better. It's going to get worse because we heard a lot of these talks throughout the day. We are going to use agents that are going to do more AI and do better AI, but we expect these agents to reason and hypothesize and carry out experiments. And as a result, when we are talking about LLM inference and other type of inference taking a lot of energy, they are going to increase by 10 to 100 folds, because most of the knowledge benchmarks that people have, created, the leading solutions on average need, and they are not necessarily very good either. those need around 40 or so calls. And many of them, often and soon we will see more and more, are going to involve reasoning models that are basically trying many more things in parallel and picking the best answer. And we don't necessarily know how things will end up, and people were creating all these estimations. So a few years ago, we started thinking about how we can understand how much energy goes before we start investing all this money that people are putting in building these new AI data centers. These are some of the news. It's very hard to keep updating. I would have put the Broadcom news over there because that was announced after I sent the PDF of the slides out. So if I wait 2 more days, there will be another news with another more gigawatts and billions and hundreds of billions, trillions dollars. It's unclear how these things will pan out, but there is a lot of investment going in. And today, AI progress is gated primarily by power. It's not by money, it's not by lack of chips, it's just we don't have enough power to power all the chips that we want to put in. Everybody has a lot of money, supposedly. I don't know where it's coming from, but they don't have enough power to connect them. And we have 2 ways of solving this problem. One is increasing energy supply. I'm sure you have also seen this type of headlines that US, actually, it is true, they are slowing down plants when they're going to shut down different coal plants. And then Microsoft, Google, everybody is trying to, turn on nuclear power plants or SMRs to get more energy so that we can connect more GPUs and more accelerators. The other side is where I come in, we come in. We've been doing this project called the ML Energy Initiative for 5 years or so. And we are trying to figure out, instead of, or in addition to, increasing energy supply, how can we reduce the energy demand? And so the goal of ML Energy Initiative is to not estimate, but very precisely understand how much energy is going into AI, for AI training, for AI inference. And we also want to go ahead and understand how to optimize the energy consumption, how can we reduce them, and how can we better facilitate performance and energy trade-off so that we can save energy consumption by slowing things down if it doesn't really impact the applications we care about, or by giving up some accuracy. Maybe our application is fine with being 0.01% less accurate. And today, or before this set of projects that we have done, there were no easy tools to measure or optimize or navigate the trade-off between time and energy. So just to give some examples, and I'm just going to go through them really quickly. I don't have much time, and I'm not going to make you read the whole plot. The point of the plot is we have been building this tool. This is completely in software that we have built, a tool called Zeus. It's a very large open source project at this point that is being used by NVIDIA and has been supported by GitHub and Mozilla and many other companies, where we can now precisely measure what is the energy consumption of all of these open weight models for chatting, for code generation, for multimodal modeling, for image video generation. And y-axis is the energy consumption on average of one of the queries that we have in our benchmark. And x-axis is, of course, all of these models. The takeaway here is that in the y-axis, if you look at, it varies widely, but it's much smaller for LLM than image or video generation. The reason I'm mentioning it, oftentimes you will read a news and then you will hear that, okay, LLM is going to consume these and that. It turns out that even if LLM they cannot really consume all the power a GPU can draw because they are often memory bound. And then they can't really keep all of the computation power of an accelerator busy. It depends on the input and so on and so forth. But on average, in many cases, they cannot. And so as a result, many of the outlandish claims about LLM's energy consumption being these and that, many of them are actually off by 2 or 3 times, which is better, but it's not great. It is lower than what people think it is, but it's also not 0. And when you multiply it by billion of users and times 10 or 100 for the agents, it only gets worse. And one of the good part of doing all of these measurements and understanding is that we can actually quantify what is going to happen when we start using all of these AI agents for science, where we throw these science problems and let the agents go wild without any control and trying to figure out. What we found, a reasoning model, a single call, and actually this is a smaller reasoning model that I have here, Qwen, that's 235 billion parameter with 22 billion active. And Llama 3.1 dense model, 405 billion parameter, it can consume about 30 times more energy just for a single query, for the same query on average. And so when we are going to use AI for science, we need to start thinking of some ways how we can, guide it in some way and not just allow it to brute force and try things out, to avoid having whatever the energy consumption is, times 10 or times 100 for how many calls we are going to make, times 10 or 30 or whatever that is going to be. So there is a potentially 1000x gap between what a single LLM call is versus allowing, an agent to use many, many AI calls and try to figure things out. So we have to be very cautious and careful while we try to have AI for science and AI solving all the problem and replace all the scientists. So that's good. What can we do about it? Before going to go there, I forgot about this slide, but essentially this is the title that I said I'm going to talk about. Without energy optimal AI agents, we cannot really have sustained scientific discovery with AI. If we want to use AI extensively in scientific process, we need to figure out how to reduce the energy consumption of single AI calls and then collection of them and agents. And then we will have enough power and energy to actually do something big. Otherwise, it's going to fall short every now and then. And I'm just going to give a quick rundown of the works we are doing to try and optimize those things. All of which work many years in just single slide. What it shows in the left top, it shows actual computation over time for training LLM. And the colors there show what is the power draw when the training is happening. What we have created is a system that can take such a training program that is running and precisely set the frequency of individual GPUs at precise points in time. Both of the figures show the same thing, but the colors are much lighter in the bottom right. What is happening is that all of the computation are running slower, but not so slow that the overall computation, the critical path is shown in blue in both of the figures, becomes slow. So essentially, we can save up to 30% energy consumption without any slowdown of your training time and without any accuracy loss. It will do exactly the same computation in exactly the same amount of time. You will just save a lot of energy. And this is on a per iteration basis when you are doing a very large model training. And then in terms of navigating and facilitating the time-energy trade-off, we also found this plot is showing x-axis is time and y-axis is energy. And each of the points are different hyperparameter combinations at the system level when you are training. And the yellow line is showing the Pareto frontier. That's showing that those are the points at which either you have to give up on some energy or give up on some time. Otherwise, you cannot, pick another point. And we found algorithm that can pick and find sort of the Pareto frontier and pick a specific point that a user care about. You could say, I care about energy more, time more, or whatever else. You can then pick and choose a point, and we can find it for you. And you can, if you're willing to give up some time, you want to be a little bit slow. And again, without any accuracy loss, we can allow you to pick a point over there, and in some cases, you can save 76% of energy consumption. And all this is for training. There are a bunch of works we are doing for inference, and many other people in different places. They are also working on inference energy consumption as well. And all of this research have led to a lot of talking points and a lot of articles where people are getting more and more aware that we need to not just solve the problem by throwing money at it, by building more, I don't know, power generators and such, but also actively trying to improve the whole stack where the hardware and the software and the application and the users of the application, the scientists perhaps, are more aware and they are trying to actively minimize the energy consumption. And this has also led to impact directly where Google recently talked about what is the energy consumption of Google Gemini. And there they sort of took our methodology and extended with additional sort of things that we didn't consider because we didn't have a whole data center in front of us when we were working on it. And it also led to us working with a lot of journalists for 6 months, actually, from end of 24 to mid 25 to, I don't know, create this big article where they had an expose on the precise energy consumption of all of these open source model that we are using. And what you can do is when you get a chance, ask like how much energy did the AI model consume? And if you keep asking, eventually like Google, everybody will start giving out some numbers. It will come in drips, but eventually there will be some water in those faucets because OpenAI, Sam Altman also talked about, okay, this is how much energy we consume because people keep asking these questions. And the other part is if you do get to know, then make a choice in terms of how to pick AI services that are more energy conserving. They might both be doing roughly the same thing, but some might be more efficient than others. And that way you can help, I don't know, yourself because it might affect you directly or indirectly. It also helps them because energy cost is operational cost. So when things are energy minimizing, that reduces the cost, then the AI services at least could be either cheaper for the users or will make more money for the providers, or both. And so with that, I'm going to conclude. This is a joint work by a lot of people at the University of Michigan, led by my superstar PhD student, J1, and then a lot of other PhD students, many masters and undergrads, some of my colleagues. And we've been, and we continue to work on making sort of all of these companies informed and aware that you can actually measure. So there is no thing about, okay, it's very hard, it's not. And then you can actually optimize, and it's actually good for you to optimize because it will be cheaper for you and everybody else. And we should focus on not simply improving accuracy, simply improving time. We should also consider energy as a first-class primitive. So all the models and all the works we are doing, we should think about how can we do the same thing. I'm not saying not do it, do it, but how to do it in an energy minimizing way. Thank you, and I'll be happy to take questions. Hi.
Very nice talk, thank you. And why did the Quen model that is less parameters consume more energy than the Llama model, which was heavier?
That's a very good question. So essentially, it depends on like how much energy a model is going to consume is roughly, I don't know, related to how much work it has to do. So reasoning model often ends up creating more tokens because they are trying to reason and consider, and then they want to give an answer. They have this internal thinking process. So they end up doing a lot more computation. Even though each of the steps are could be a little bit smaller, but the number of tokens they have to produce to get to an outcome is many, many times larger. So overall, it ends up consuming more energy. Similarly, say, for example, between LLM and image or video generation or image generation consume a lot more because they are extremely compute heavy. And so to generate an image, an average image, it will likely consume many times more energy than generating an answer in text.
So choosing the right model for the right function can really dramatically reduce the amount of energy.
This is a very good point. Thank you. So choosing the right model for the right task. We shouldn't just have that this is the best model and throw everything to it. We should have a way to decide. It could be human deciding. It could be an automated router. Many of the inference service providers nowadays have a router where you request go, and then they route it to a model that is commensurate with the complexity of the task and not necessarily just throwing everything to the best and greatest model. So that will also actually save a lot of energy. So in some way, even though they are not necessarily doing it for energy, they are doing it for reducing their cost and response time. It is also reducing energy, and energy, as I said, reduces operational cost. So it's all sort of related.
Thank you.
Hi, Karthik.
Yeah. So how much of your optimization is dependent on, in these cases, you have a finite vocabulary and transformers, right? But thinking more on scientific applications, thinking of diffusion models, neural operators, how much leeway do you see in those kinds of architectures for optimizations?
Thank you. This is a very good question. So the optimization that we do are at the systems level. So we actually do not know much about how AI works and what the models are trying to do. What we look at is when you have a model and you are trying to train or do inference and you distribute it across multiple GPU, how the work is distributed and partitioned. If you could have very balanced partitioning, then we don't have as much opportunity. And when you end up with some imbalance, we will have a lot more opportunity. So the more imbalanced the distribution of work across multiple accelerators are, the more opportunity we have. Now, what models have more imbalance, it becomes a function of the architecture of the model. Some models have, for example, in case of transformer, you have these replicated transformer blocks one after another. They are all the same, except for the first embedding layer and toward the end, the heads. You don't really get much opportunity. So actually, for some of the other models where inherently you ended up with some imbalance in different layers, because as a ML person, you are probably not even considering like what is going to happen to anything else. I just want my job done well. And then if it ends up being somewhat sort of skewed, then what our software can do without you having to do the dirty work, we will figure out how to handle, sort of assign work and frequency sort of scheduling so we can save the energy. So it's a function of.
Yeah, if I may just add a sub-question there. If I flip the question and say, what is it that we can do, right, to take advantage of some of these optimizations you have, what would you advise to model developers?
Thank you. Again, a very good question. So as I said, that the tools that we have built, Zeus, this is, I keep talking about AI and LLM because this is the model of the day, but essentially it's for any deep learning neural network. You can apply to anything that runs on a GPU or CPU. We can use it to measure. And in terms of optimization, like as long as you end up with a computation graph, which is going to be a directed acyclic graph or a DAG, then the algorithm is agnostic. It can take any DAG, and then it can set the frequency, and it can control at that level. And I know that it's probably will work for many of the models, because most recently, NVIDIA actually reached out to us, and then they tried it in a hardware that we don't have and in a model that we didn't run, and then it did manage to run like without many hiccups, and then they did manage to, I don't know, get it up and running. So the first step would be, if someone wants to use, is just using the tool just to measure. So when you have your scientific results, you can also say, okay, we did this, and this is how much energy it consumes, so people are informed. Because right now, even if you ask me, okay, Mosharaf, is 2000 joule very high or is it very low? I also don't know. I have to do a calculation and figure out, okay, it's like lighting a bulb for 1 hour. But as everybody keeps talking about these numbers, then people will slowly get familiar, okay, it looks high. And then you would say, okay, now go back and redo, and how can we minimize it? So the first step would be just informing. And then like the tool usage-wise, it is general purpose. And as I said, that we have a bunch of people who are very dedicated and care about the project a lot. So if you try to use and get stuck, if you create an issue, somebody will get back to you, I don't know, probably within 24 hours that, okay, what is the problem and how can we, I don't know, help you?
Thank you so much.
Thank you.